Hello everyone, welcome back to the channel. Today we have a quick tip on how to apply develop flow profiles at the inlet of your domain. Whenever we're looking at flow that is entering a pipe or a duct from a source, the flow profile through that pipe takes some time to develop. So as we know, in most cases we'll have a no-slip condition along the wall, and over time as the flow progresses through the pipe, it will eventually form this parabolic profile for laminar flows. The one thing to note, though, is that this profile, to be fully developed and fully set up inside your pipe or duct, it will take a bit of time. We can actually calculate how much pipe your fluid has to flow through before you get this fully developed parabolic profile. And we have these empirically derived equations. So for laminar, the entrance length is going to be 0.0575 times the Reynolds number times the diameter of the pipe. Similar for turbulent, it's going to be 1.359 times your diameter of the pipe times the Reynolds number to the 1/4 power. So each of these, if we go through and calculate, will tell us how long we have to simulate our pipe before we get this fully developed profile. So whenever we're simulating big industrial systems, what we usually do is segment those systems to look at the specific components that we want to do our simulation on. And the piping in between those components usually isn't of interest. We don't want to waste time simulating the flow through those pipes that connect our different components. So to do that, we usually segment our model into these individual components, which we can look at in much higher fidelity than if we had to simulate the entire system as a whole. What happens in that case, however, is that we end up cutting through our inlet and outlet piping, and that can sometimes lead to some inconsistencies when we're simulating these components. And to overcome that, what we can actually do is apply the boundary condition or whatever flow condition we're getting from the piping into our component of interest to make sure that the component that we are simulating is going to be simulated with the highest accuracy possible. There's a lot of different ways to apply these profiles, including UDFs, using a CSV file to define a profile. The way I'm going to show you today is what I think is the easiest way, and avoids a lot of the calculations and headaches that come with using UDFs. So I'll hop over into Fluent and I'll show you how to set that up. So in Fluent, I just have this simple pipe flow. It's 200 millimeters long and it's 30 millimeters in diameter. You can think of this as maybe the entrance to a pump or some other component that we're going to look at. Right now we have the inlet defined as a velocity inlet with a velocity magnitude of 2 meters per second. If we look at what the cross-section velocity looks like through the pipe, we can see that we have our inlet on the right here, our outlet on the left, and we can see that our flow is nowhere close to being fully developed. So we're gradually forming the boundary layer here as we get to the end of the pipe, but we're still going to need way more length of this pipe before we achieve that parabolic profile. So if we did have a component on the side here and we were using this inlet profile, we may be missing some resolution or fidelity that we may want out of this model. So the simplest way I've found to apply this profile is by using expressions. And we can set expressions by coming up to the user defined tab, and we'll make a new named expression. So the first expression we're going to make is going to be called U max, and this is going to be the max velocity at the top of our profile. In this case, we'll make it 4 meters per second and go ahead and click OK. So the next thing we'll do is we'll create a new named expression. This first one we're going to call radius with a big R. So we're going to define this as the square root of the area of our inlet over pi. So we can type square root, we'll type area, and then we can add the name of our inlet. In our case, it's just called inlet. And then we're going to divide that by pi. The next expression we're going to define is radius with a lowercase r. And in this case, we're going to convert our XY dimensions to our radial dimension. So we'll start by typing square root. We'll take our X dimension and square that. And then we'll add it to our Y dimension and we'll square that as well. The last thing we're going to do is we're going to make our expression for our inlet velocity profile. So we'll make our final named expression. We can call this U profile. So this profile is going to use our parabolic profile. And we're going to define this with the equation of U max times 1 minus radius with a small r divided by radius with a big R. And then we're going to square, go ahead and refresh that and click OK. So now if we go back to our inlet velocity profile in the boundary conditions, we can come down to the velocity magnitude and hit this drop down. And we'll now see we have this U profile that we can define for our velocity magnitude. So we'll go ahead and select that. We'll click apply and we'll recalculate the simulation. So we now reran our model with that inlet profile, and that we can now see that we have a fully developed profile starting directly at the inlet and going all the way through the pipe. You can see our boundary layer is fully developed all the way down the length of the pipe. And again, if we had any components here, or if we were looking at heat transfer or anything else on this system, we would now have a much more accurate simulation where we take into account that entrance length and the development of the flow through the pipe. If you have any questions about this setup or any simulation that you're working on, feel free to leave those in the description. And if you'd like to support the channel, please hit the super thanks button below. I really appreciate it. Thank you.